Well, welcome back again. It is for those who watched the first video that I recorded yesterday. This is to let them know that it took me 5 days to create, present and record that video. I locked myself into a room while I was recording that video. It took me 3 hours to produce and upload it to YouTube. Well, all this time I kept my wife and my kids locked out of my room. And once the video was all set on YouTube, I presented it to my wife, and to my surprise, after watching it for 1 hour and 38 minutes, that's the runtime duration of that video, she said it was very boring. The number of criticisms that I got from her were more than the number of slides I presented in that video. She said it is boring, it lacks energy, it is not my natural tone and voice, it feels I was talking to a computer and not to the audience, there was no connection and feeling in the video. See, 4 slides and 5 criticisms. I knew she was not happy either, saying all these bad things about my work. But as Shiv Khera, the famous motivational speaker, once said, accept criticisms as long as it is a pain to the giver. And now that I am married to her for last 10 years and every day I need to go back home, where she is less of a wife and more of a critic to my work, I thought of making this part a little more energetic and natural. So let's get started. I am on to this next topic now, which is PGA and database instance connection. So let me first explain the program global area, also called as the private global area, in short. Now the reason for keeping it short is a more broader discussion would follow on the coming slides. So on this particular slide, I'm going to keep it real short. So to describe program global area, like any program that you run, any program that you execute, it would be loaded into RAM. The program might also need to define certain variables and data structures for its working. Now these variables and data structures would also need some memory at runtime. Now such a memory area associated with any background process and a server process which is privately held by that owning process is what is called as PGA, the program global area or the private global area. So if you see here, for the various different background processes such as dbwn, the log writer, the smon, or for that matter any server process that I run, they would need, each of these process would need its own privately held memory which is non-shareable in nature. This is what is called as the program global area. So many different. So as a whole, in short, for every running instance of your Oracle database, there would be exactly one system global area, but there would be many program global areas, because program global area is process specific. That is the memory which is not shareable, which is very privately held by a given background process. So this is the short introduction to PGA. Let's move on to understand the SQL statement processing and how it works. But before any user submits a SQL statement, to be able to do so, there are certain prerequisites. Those prerequisites are: the user must have a valid database session established. So on to this right hand side of my slide, I'm going to quickly explain how the whole thing works from the point a user initiates a connection. So this is any user who uses some kind of an application software. That application software might be developed by your own developers, or it might be any other tool available from Oracle like SQL Developer, or it could be a tool as simple as SQL Star Plus. The very first thing a user does is to request a connection with your Oracle instance. Your Oracle instance is running somewhere on some server machine, somewhere on your network. So this is my host, and this host is running my database instance. The user types the necessary login credentials in the tool, like say SQL Star Plus. A user might say, use SQL Star Plus to connect me in as Scott, password as Tiger, @ some connection string. That connection string somehow would resolve to this particular host and to this particular listener running on this particular host, and would request a connection to the given instance. So my client, by providing the login credentials, inadvertently is making a connection request, which ends up with a listener process here. A listener is a special process running onto your database server, which continuously listens for incoming client's connection requests. So somehow, let's not worry what is the background logic of it, because sometimes during one of the architectural discussions I am going to also talk about the network configuration files, both for the server where the listener is configured and for the client where the client comes to know which particular listener is to be contacted when the initial connection has to be established by providing the necessary credentials. So the user somehow has provided the necessary login credentials, including the username, the password, and the connection string. That connection string somehow has resolved that it needs to reach to this particular server in the network, and there's a listener process running on to this particular server. The listener typically listens on port number 1521 using the protocol TCP. So this connection, which is initiated via some user process, hits the listener saying, hey, I am interested in connecting to this particular database instance. Would you facilitate the initial connection making part? This is what is the request that comes in from the user to the listener. The listener, depending upon the configuration of your instance, as I said in one of the slides, your instance could either be configured in a dedicated mode or your instance could be configured in a shared server mode. So assuming that my Oracle database instance running on this machine is configured in a dedicated mode, the listener contacts the instance. The instance then picks up or starts a new server process which is very dedicated to this particular user process. It passes on the address or the listening location of this server process back to the listener. The listener forwards that particular address to this user process, and once the user process knows where to go, going forward for all the requests that it's going to place, it's directly talking one-on-one with this server side equivalent of it called as a server process. This is what happens during the dedicated connection. But what if you have configured the Oracle instance in a shared server mode? Well, in that case, for every user process, there wouldn't be a server process on the server side. It's somewhat different in that case. So my user placed the necessary connection authentication details. My user process has reached somehow to my listener. My listener knows that this particular instance is configured in a shared server mode. So it contacts the instance asking for an address of a dispatcher process. The dispatcher process's address is passed on to the listener. the listener passes on this particular address of the dispatcher process to the user process. Going forward, my user process, as you can see here, can directly interact with the dispatcher. There is no more a role for my listener to play as far as my this particular connection is concerned. So irrespective of whether I have configured my instance in a dedicated server mode or in a shared server mode where there is a dispatcher process, the role of a listener is only for the initial connection making part. Once the listener forwards the address of either a dedicated server process to the user process or the address of the dispatcher process to my user process, going forward, my user process can directly interact with the server side equivalent of it, which in a dedicated server environment is a dedicated server process and which in a shared server environment is a dispatcher process. Now assuming that my user has placed some SQL statement in a dedicated configuration, the server side equivalent, which is dedicated for me, would pick up that request, would process it in some way and would place back those results back for my user process over the network. And my user in that tool, I am assuming it's a SQL star plus tool, would see the necessary outcome of his SQL statement. On the other hand, if I am running my instance in a shared server configuration, after the initial connection has been established, now there is a one-on-one dialogue between my user process and the assigned server-side dispatcher process. My user places a request. The request is picked up by my dispatcher process on the server side. It would pick up and it would put that request for processing into something called as a request queue. A request queue is an in-memory data structure and the memory for the request queue is allocated from the large pool. Large pool itself is part of your SGA. So the dispatcher puts that request into the request queue. Irrespective of the number of dispatcher processes you might run, there is exactly one and only one request queue. So all those dispatchers are going to place their request which they have received from the users into the same request queue. Now a DBA would have defined how many shared server processes your instance would start at any given point using some init.aura parameters. So one of the free server process, which is actually a shared server process because these processes are shared by many connected users to your database instance. So one of the shared server processes would pick up your request from the request queue, would start processing it in some way here. Once the processing has been done, the shared server process is going to place back the results into something called as a response queue. Now response queue is another in-memory data structure, the memory for which is allocated again from large pool, and large pool in turn is part of your system global area. So the shared server process has put in those outcome or the output into the dispatcher specific response queue. So understand this thing very clearly. Irrespective of the number of dispatchers, there is exactly one request queue. But as many dispatchers as you would have on your system, those many response queues would be available. So depending upon from which dispatcher the request was received by my shared server process, the shared server process would put in the output into that dispatcher specific response queue. The dispatcher then reads this queue, forwards the outcome back to the user process. Now a session is a representation of a specific login by a user and it's typically a time frame from the point the user got connected till the time he disconnects from the database instance. So this is overall how the connection is established. Now the reason why I brought in this particular topic here is because on to the subsequent slides I am going to talk about SQL statement processing, and for that the prerequisite is the user must have a valid session with the database instance, and this is the particular flow of how things work behind the scenes so that a user can establish a valid session before he places a SQL statement for processing. I'm going on to the next slide. Here I'm going to talk about how exactly the SQL statement processing happens. Now you see this diagram talks about PGA, the program global area, which is the private memory of a given server process, or for that matter any other background process for that matter. So this is my server process on the server, and this process would require its own memory for its operation, which is exactly what I described here as PGA. As there would be many server processes, for every server process there would be exactly one PGA. So there are many different PGAs for a given database instance. Now just look into this PGA and you would notice that there is this area called as SQL work areas, which includes the sort area indicated by an alphabet S. Then there is a hash area indicated by an alphabet H, and then there are bitmap merge areas indicated by BM. They are all part of the PGA memory, and collectively these areas are termed as SQL work areas. Apart from SQL work areas, you would have session memory and you would have private SQL areas. And as I said, apart from this, you also have a larger memory allocation called as the system global area. Unwanted elements of SGA, I have already phased them out, never put it into this slide. The other memory components that are missing here are database buffer cache, large pool, streams pool, Java pool, redo-log buffer, and whatnot. I have eliminated everything that is not relevant for this particular slide. So the PGA is a memory specific to an operating process, or for that matter a thread, that is not shared by other processes or thread running onto the system. Now because the PGA is very process specific, it is never allocated in the SGA. This is point number one. Now the PGA is a memory heap that contains session dependent variables required by a dedicated or a shared server process. The server process allocates memory structures that it requires into the private global area, PGA. A PGA is subdivided into different areas. Each of these areas serve a different purpose throughout the life cycle of your SQL statement processing. And not all the PGA areas will exist in every case. Some of them may be there, some of them may not be there, but more on it at a later time. A private SQL area, which is indicated here, holds information about a parsed SQL statement and other session specific information for processing. When a server process executes a SQL or a PL SQL code, the process uses the private SQL area to store the values of bind variables and also the state of your query execution, along with the work areas, which are called as the SQL work areas. Now I want to remind you that do not confuse a private SQL area indicated here, which is part of your UGA memory, with the shared SQL area The shared SQL area is indicated as part of shared pool, which is allocated in library cache in your SGA. So don't get confused. These are private SQL areas which are in PGA in case of a dedicated server configuration, whereas the shared SQL areas are part of your library cache, which in turn is part of your shared pool, which in turn is part of the system global area. So say for example, you run 20 different times select star from EMP as one of the SQL statement. So in one session and 10 executions of the same query in different sessions, they can all share the same shared SQL area, but each one of them would have their own private SQL area. Just to elaborate it a little further, example, assume that this is particularly the session initiated by some user called as Tom, and this is another session by some other user connected from a different client machine, let's say Jack. They both are connected and they both ran a SQL statement, say select star from EMP. Now that's why they both are pointing to the same shared SQL area, which is in my SGA, but despite the fact that they are sharing the same shared SQL area memory in my SGA, still they would have their individual private SQL areas. Whereas in this third case, I am assuming there is another user called as Dick who has run a different statement. That's why his particular pointer points to a different shared SQL area and not to the same one, because his statement is somewhat different than those which are fired by Tom and Jack. So every single unique statement that you fire would need a shared SQL area, but irrespective of the statement being same or different, each server process would still have its own private SQL area part of PG. Now here there is some interesting part. So this is my client process. The client process also requires some amount of memory, which is the data area. That data area contains a pointer. This is onto my client process. This pointer points to my private SQL area, which is in my server processes PGA memory allocation. This pointer is what is called as a cursor. Yesterday I have given you the definition of a cursor, which stands for current set of records. So a cursor is nothing but a name or a handle to a specific private SQL area. You can think of a cursor as a pointer on the client side and as a state on the server side. And because cursors are closely associated with private SQL areas, many a times you would see the private SQL area or the cursor terminologies being used interchangeably by many different people. A private SQL area internally, although it's not shown in my diagram here, but this private SQL area is also divided into something called as a runtime area. A runtime area contains query execution state information. The runtime area tracks the number of rows retrieved so far by a given statement. So the purpose of that runtime area is to keep on counting how many records have been retrieved, how many of them are still pending. The Oracle database creates the runtime area as the first step of an any SQL execution request that you put in through. The very first statement is to create this runtime area. For DML statements such as insert, updates, deletes and merge, the runtime area is freed the moment the SQL statement is closed. Apart from the runtime area in your private SQL area, there is something called as a persistent area. This persistent area contains values of bind variables. A bind variable is supplied to a SQL statement at runtime when the statement is executed. The persistent area is freed only when the cursor is closed. So there's a small difference there, as I said. So within private SQL area, always remember there are two smaller memory allocations, the runtime area and the persistent area. The client process indicated here, I think I should better draw a pointer, a highlighting laser pointer. So this is my client process, and this is the memory of my client process in the gray rectangle, and there exists a pointer which is called as a cursor, which exactly points to the private SQL area, which is the memory allocated from within the PG of my server process allocated for me, since I am talking about a dedicated server configuration. So this pointer points to this area, which is what exactly is termed as a cursor. So the client process is responsible for managing the private SQL areas. The allocation and deallocation of the private SQL areas depends largely on the application. Although number of private SQL areas that a client process can allocate is limited by your initialization parameter called as open_cursors. Although mostly users rely on the automatic cursor closing mechanism and the database intrinsic facility to close the cursor whenever it is not required, the Oracle database programmatic interfaces are available for developers, whereby a developer could explicitly write a close cursor call. I'm going to show you on one of the subsequent slides how using the DBMS SQL package one can explicitly close a cursor whenever it's no longer required. In general, application should close all open cursors that will not be used again to free the persistent area and to minimize the memory overhead required by the application's user. This is one of the good development practices recommended for the developers. The Oracle database recognizes when two users execute the same SQL statement. As I said here, this is my server process allocated to a user connection initiated by, let's say, a user named Tom, whereas there's another user who initiated a connection named Jack, and this is the server process assigned to Jack. Now I'm assuming both Tom and Jack ran the same SQL statement. Now Oracle has this ability to identify whether the statements are identical or not identical. This is by computing something called as a hash value. So the Oracle database recognizes when two users execute the same SQL statement and it reuses the same shared SQL area for all those users. So that's why Oracle never allocated more than one shared SQL areas here, since both of them ran the same SQL statement. However, each user must have a separate copy of the statement's private SQL area. So it would, irrespective of we pointing to the same shared SQL area, because our SQL statement is same, despite this fact, the PJ would still hold the private SQL area independently for the user named Tom and for Jack into their respective server processes' private global area memory. A shared SQL area contains all optimization information that is necessary to execute the statement, whereas a private SQL area contains all runtime information that is related to a particular execution of that statement. Oracle database saves memory by using one shared SQL area for SQL statements that are run multiple times. Multiple runs often happen when many different users run the same SQL code. Now there's another interesting point also about that Oracle database creates and uses memory structures for various different purposes. For example, Memory stores program codes that are run. It also stores data that is shared amongst various different connected users, and private data areas for each of those connected users, basically referring to a portion of memory that is never shared by the processes amongst themselves, which is PGA. The Oracle database allocates memory from the shared pool when a new SQL statement is parsed to store in the shared SQL area. The size of this memory, which is for the shared SQL area, depends on the complexity of the SQL statement that one has submitted. If the entire shared pool was already allocated, the Oracle database can deallocate items from the pool by using something called as a least recently used algorithm, LRU algorithm, until there is enough free space available for new statements to allocate their shared SQL area. So I'm assuming there was no free space left in my library cache. Then in that case, Oracle will phase out, flush the least recently used shared SQL areas from the memory, and it would keep on doing the flushing activity until sufficient memory becomes available so that my new statement can allocate its own shared SQL area in my library cache. If Oracle database deallocates a shared SQL area, the associated SQL statement, if somebody runs the same SQL statement again one more time, then again a hard parse would be required, or a reparsing would be required, and reassigned to another shared SQL area as it is being executed for the subsequent time. So assume that there was no more free space left, and depending upon the LRU algorithm, this area was deemed unwanted. Oracle phased it out. Now there is no longer this particular shared SQL area available. This memory was allocated to someone else. Now some other user runs the same SQL statement. It checks into that whether there's a shared SQL area available. It was available until now, but now that you have flushed it out, the user who submitted this statement, the SQL statement would require a hard parsing again. Again, Oracle would allocate, by freeing up some memory if it is not already available, some amount of memory depending upon the complexity of my SQL statement. It would allocate shared SQL area, and then it would begin the hard parsing process, which is very time consuming, as I'm going to describe it on to the next slide. So this is how overall the PGA and the SGA, or the shared SQL areas within library cache, within shared pool, within my SGA, interacts with the private SQL areas within my PGAs. And as I said, for every instance you would have only one SGA, but there would be many PGAs, and collectively all these PGAs are called as instances aggregate PGA memory allocation, which also is controlled by the init aura parameter PGA aggregate target. So you cannot limit the individual PGA memory regions, but collectively you can mention what is your memory budget for all the PGAs taken together, and Oracle would check this PGA memory allocation and the memory consumed by all the PGAs every 3 seconds. The moment my collective memory usage by PGA exceeds my parameter, Oracle is going to do the memory release activities for the PGAs. But more on it at a later time once we go on to 11G new feature called as automatic memory management. More on that, how the memory resizing, reshuffling happens. More on that at a later time. So let's move on to the next slide. Now this is where I'm going to talk about a lot of things. Now since my wife said that your presentation of video 1 was pretty boring, to make it a little more interesting, I brought this pretty little girlfriend of mine. This is my user. who submits a SQL statement, and the purpose is to understand what happens during parsing, because this is mostly the dreaded phase by all those who look into the performance tuning aspect of it. What is parsing? Before I get into the technical details of parsing, let's understand what is the dictionary meaning of parse as a term means. By parse, we mean to analyze a statement or a sentence in terms of grammatical constituents, identifying the parts of speech, syntactic relations, etc. The other definition is parse is to describe a word in a sentence grammatically, identifying the part of speech, inflectional form, syntactic function, etc. So basically, parsing is a process of doing a thorough analysis of what has been written. So my girlfriend submitted a SQL statement. Oracle does not know head or tail anything about the SQL statement. Now Oracle needs to know more before it actually begins processing and it fetches in the required details back to me. So it needs to know more and more details about my SQL statement. This is where the parsing phase of SQL statement processing comes in picture. So the SQL processing consists of many different stages. Broadly speaking, it includes parsing, optimization indicated here, row source generation, followed by execution. Well, some of you might object saying why I didn't show the fetch stage, because that's not my focus area as of now, because I want to stop right at the execution phase. I don't want to go beyond the execution phase to talk about the fetch, since my focus is to understand what exactly parsing means. So beyond this, there is one box that is missing called as fetch. This is the time when my girlfriend would receive all the output of my SQL statement that she fired some time back, and I, being a good DBA, trying to explain what happens from the time she submits her SQL statement, what all things goes back in your Oracle database instance till execution. But beyond execution there would be fetch, and this is the time when she would receive the outcome of the SQL statement that she had submitted to the Oracle database instance. So broadly speaking, as I said, there is parsing, there is optimization, there is row source generation, and then there is SQL execution, and beyond that, as I said, there is also fetch. So let us focus on the SQL parsing phase. The SQL parsing is the first stage of your SQL statement processing that involves separating the pieces of SQL statement into a data structure that can be processed by other routines. When an application issues a SQL statement, the application makes a parse call to the Oracle database. By database, I am assuming database instance, because you are never connected to a database. You are always connected to some server process or to some dispatcher process, which is part of an instance, not as a database. But as a general analogy, that your application would make a parse call to the Oracle database instance. During the parse call, the Oracle database instance performs many different actions, such as it checks the statement for syntactic and for semantic corrections or validity, represented here by syntax and semantic checks. Beyond that, it determines whether the process or the user issuing the statement has necessary privileges to run this, which is part of your privilege checking. Then it allocates private SQL area This is the allocation of private SQL area. Remind you, in the dedicated server configuration, private SQL area is allocated in the PGA of the server process. Whereas in case of a shared server configuration, the private SQL area would be allocated in the SGA itself. Not within SGA, within the library cache itself. SGA would be too generic term to say. So within SGA, within shared pool, that particular memory would be allocated for even the private SQL areas. So your instance allocates private SQL area for your statement. It determines whether or not there is an existing shared SQL area containing the parsed representation of the SQL statement that you are running already available in the library cache. If so, the user process uses this parse representation and runs the statement immediately. So I am assuming that my girlfriend submitted a statement which is very unique and was never run by anybody in the recent past. So Oracle computes the hash value of the SQL statement. It allocates, it has taken my statement through syntax semantic check, privilege checking. It has also allocated private SQL area. Then it checks whether this statement is already available in the shared SQL region. The shared SQL region is part of my library cache, which is part of shared pool, which is part of SGA memory. And if it is already present, then I don't have to do the optimization, I don't have to do the row source generation, because somebody before her has already done the optimization and row source generation, which is already available in the shared SQL area for that particular user whenever he ran it. So my girlfriend gets benefited because there are things which are readily available, and directly from here it goes to the execution phase. Now whenever this happens, it is called as a soft parse. So understand one more time in short. The moment my girlfriend submitted the SQL statement, the Oracle instance has computed a hash value. This hash value is very unique depending upon the verbatim statement that was submitted. Oracle performs syntax semantic checks as part of parsing phase. It checks whether necessary privileges are available. It allocates private SQL area. That private SQL area may be either in my PGA or maybe in my library cache itself, depending upon dedicated or shared server configuration. Now this hash area, that hash value of my SQL statement, was checked into the shared SQL area if it is already present. If it is present, Oracle counts it as library cache hit, which subsequently results into a soft parse. It bypasses many different things and directly gets to the business of executing the statement. But assume that this statement was very unique. Nobody in the recent past ran the same statement. So the shared SQL area is not available. Oracle computed the hash value, started the parsing, allocated the private SQL area, then it started checking in my shared SQL area namespace of my library cache. If this hash value is present, the hash value was not found. Pretty bad. Pretty bad. It means one more time it has happened that I was looking for a matching hash value in a given namespace of a library cache and I couldn't find one. Oracle keeps a track of this as library cache miss, which subsequently results into a hard parse. Now in this hard parse, I would have to do everything on my own, which includes optimization of the SQL statement that was submitted. And in the optimization, the optimizer generates multiple execution plans and weighs them, compares them for their relative costs, and the one that is supposed to be least costliest would be picked up as my final decision of the way I am going to execute my SQL statement. So this is quite a cumbersome process. It's very CPU intensive. There are a lot of things that Oracle has to do in the optimization phase of SQL statement processing, which comes as part of hard parse, which is an outcome of a library cache miss, which is because of the fact that my statement is very unique in the recent past. The hash value never matched to any of the recently executed statements. From optimization, there's a next step which is again very time consuming, which is row source generation, again part of hard parsing. In the row source generation, it generates query plan with many steps where each step produces a row set, and then it moves on to the execution. So obviously you are taking a longer route: optimization, row source generation, part of hard parsing, and then going to the execution, as against bypassing these costlier phases and directly coming to the execution phase. This is what exactly is a soft and a hard parse. Just to quickly sum up, during the parse phase, the database performs a shared pool check to determine whether it can skip the resource intensive steps for statement processing, namely the optimization and the row source generation. And you can prove it by looking into dynamic performance view called as $SQL. There is a column by the name SQL ID to find out from the recently executed statement what is exactly your statement looking like. So note there's also a difference between an application making a parse call for a SQL statement and an Oracle database actually parsing the statement. A parse call by the application associates a SQL statement with a private SQL area. After a statement has been associated with a private SQL area, it can be run repeatedly without your application making a repeated parse call again and again. Whereas a parse operation by the Oracle database instance allocates a shared SQL area. I'm assuming it's a hard parse because shared SQL area allocation only happens for hard parsing. For a soft parsing, that area must have been allocated even before by some other user who would have ran that statement for the first time. So for that particular user, it was a hard parse. For you, you don't have to allocate the shared SQL area. It's already being allocated for you. After a shared SQL area has been allocated for a statement, it can be run repeatedly without being reparsed again and again. Both the parse calls made by the application and the parsing that is being done by your database instance can be very expensive operations with respect to when I compare it with the execution phase. So perform them as rarely as possible. So as a tuning goal, we always look at the library cache hit ratio, which describes out of 100 statements that you have submitted till date, how many times you had to do a hard parse, how many times you had to do a soft parse. Oracle recommends that ratio to be 99% and beyond, which means out of the 100 statements, 99 times it should result into a soft parse. Exceptionally, in certain cases, you may have to do a hard parse. But too many times doing a hard parse is not good from the performance standpoint. Although parsing a SQL statement also validates that statement, parsing only could identify errors that can be found before executing the statement. So not all type of errors can be captured here. Some of them can be located only when you begin the actual execution. So here only syntax and semantic checks can be could be done, and errors pertinent to syntax or semantics could be captured, but there could be errors in your SQL statements which are not captured during the parsing phase. They could only be located during the execution part of it. For example, errors in data conversion or errors in data such as an attempt to insert a duplicate value in the primary key can only be trapped during the execution. There's no way one could find it out during the parsing. So parse operation falls broadly, as I said, into a hard parse. A hard parse is like if Oracle database cannot reuse existing code, then it must build a new executable version of the application code. This operation is a hard parse, which is a outcome of a library cache miss. During a hard parse, the database accesses the library cache and also the data dictionary cache several times to check certain things from the data dictionary. When the database accesses these areas, it uses serialization devices called as latches on required objects so that their definition shouldn't be altered while I am checking certain things from the data dictionary. Latch contention is one of the primary issues behind the degraded performance as well. So Oracle does not know many things. Like somebody might have said select dname from EMP. Now dname is not a valid column in the EMP table. So Oracle issues many different SQL statements on its own to ascertain certain facts, and all these statements that Oracle issues in the background are called as recursive SQL statements. There are certain characteristics about the recursive SQL statements. Number one, a recursive SQL statement is always issued by Oracle internally. It's never fired by an end user. Second, a recursive SQL statement is always a query against the data dictionary. It will never query user objects such as EMP tables from Scott schema. It will be always a query against some data dictionary base table or a data dictionary view. Third thing, the outcome of a recursive SQL statement is always fixed. There are two possibilities. A recursive SQL statement would either result into no rows selected or at the max one row selected. There is no third possibility for a recursive SQL statement. All these queries that Oracle runs internally, called as recursive SQL statements, are predominantly part of your parsing phase of SQL statement processing. And remember, Oracle runs many such SQL statements in the background as part of syntax, semantic check, privilege checks, and many more. This is, and also as part of optimization for that matter, where it needs to find out what is the total number of records present in a table, finding object statistics from the data dictionary so that my optimizer can make more intelligent decision making, finding the histograms, which is a record that Oracle keeps in its data dictionary, which tells you exactly whether the data is uniformly distributed throughout the column or the data is skewed, means non-uniformly distributed. Now, to ascertain these details, Oracle runs many different SQL statements in the background. This is what is called as recursive SQL statements. Whereas in case of a soft parse is any parse that is not a hard parse simply. That means if the submitted statement is the same as a reusable SQL statement already available in the shared SQL area namespace of your library cache, which is part of your shared pool, which is part of your SGA, then the Oracle database reuses the same shared SQL area. This reusing of the code is possible because of something called as a library cache hit. Soft parse can vary in how much work they perform. So the number of activities that one has to perform in soft parse is also not fixed. For example, configuring the session shared SQL area can sometimes reduce the amount of latching in the soft parsing, making it even something called as softer. In general, a soft parse is obviously preferred over the hard parse because the database skips the optimization and the row source generation related steps, and your SQL statements response time would certainly improve because the two costlier phases in your parsing are bypassed and you directly jump from here to here, directly to the execution part. So obviously the next thing would be to understand what exactly happens in the optimization phase. So the SQL optimization phase, which is part of your hard parsing, and it happened because there was a library cache miss because your hash value could not be located in the shared SQL area namespace of your library cache. Here, the optimizer attempts to generate the best execution plan for a SQL statement. The best execution plan is defined as the plan with the lowest cost amongst all the probable candidate plans available. So if I ask someone, what if from here I want to go to a different, say to a super shopping located in a nearby place. There may be 1,000 different ways to go from here to there, but not all the routes are equally efficient. Sometimes, probably for a morning time, route A may be efficient, but in the afternoon, probably route A might not be the most optimal path. I should take preferably a longer route to avoid the traffic jams, and I could still reach there a little faster. So there are many probable ways to run your SQL statement, but not all the methods are equally efficient all the times. So the job of your optimizer is to tell you, out of the many different available candidate probable plans, which is the most efficient as of now. So the optimizer determines the best plan for SQL statement by examining multiple access methods, such as accessing the underlying tables with a full table scan, or by performing index scans, or by selecting from the many different join methods a nested loop method, or a hash join method, or a sort merge join method. So from the many different possibilities, the optimizer evaluates various different ways to run the statement. During the optimization stage, the Oracle database instance must perform a hard parse. Basically, it is part of the hard parse at least once for every unique DML statement that it performs the optimization during the parsing phase. The database never bothers about optimization of a DDL unless the DDL itself is made out of some DML as part of the subquery. But I am primarily concerned about DMLs and the selects that you are running. So the job of your optimizer as an intelligent body is to determine from the many different possible ways of running a SQL statement which method is the most efficient method as of now. Remember, this is not going to be the permanent method to be followed henceforward. It would change from time to time depending upon the dynamics in the database. Those dynamics are called as cardinality, the number of records in the underlying tables; selectivity, which is a guesstimate done by the optimizer to find out the percentage of records that might get filtered because of your where predicates; and the histograms, the idea that optimizer gets from the object statistics about how data is distributed within a column, whether it's uniformly distributed or whether it's grossly skewed. So depending upon these three factors, namely cardinality, histograms, and selectivity, which is exactly a guesstimation, the optimizer compares the costs of various different methods, and then it finalizes the one that is the least costliest one as of now. This is what happens during the optimization. It's very costly. If I start drilling down into the optimization phase, we can go to any level of granular details to understand how Oracle knows about cardinality. What if my object statistics are missing? Then how optimizer makes a more informed decision making? What is the role of the init parameter optimizer dynamic sampling, so that my optimizer can still make, in the absence of missing object statistics, a more intelligent decision instead of simply being misled, saying, hey, I was misled by the missing statistics. How that optimizer dynamic sampling parameter helps optimizer to gather runtime statistics to make a more informed decision making and come out with a plan that is the least costliest plan as of now. So beyond optimization, there is row source generation. In the SQL row source generation, the row source generator, which is a software code written by Oracle, that receives the execution plan, which was obtained from the optimization phase given by the optimizer, and outputs the execution plan for the SQL statement. So the iterative plan is a binary program that, when executed by the SQL engine, produces some result set. The execution plan takes the form of a combination of steps, typically seen as a indented ones, collection of steps, where each step returns a row set. The next step either uses the row set in this set, or the last step returns the row to the application issuing the SQL statement. So it may be a fairly complex plan, execution plan, which might have several different steps. I'm going to show you a quick demo onto this one as well, where each step is an action item for Oracle, and that action item in turn returns a row set, a set of records from the database. If this is the final step, the records retrieved are directly given back to your application. But if it is an intermediate step, then the results produced by this step would be clubbed with the remaining other steps in your execution plan, unless all the steps have been executed, and then the final outcome would be returned back to the user. A row source is a row set written by a step in the execution plan, along with the control structure that can iteratively process the records. The row source can be a table, it could be a view, it could be an intermediate result coming out of some of the steps, It could be a join or a grouping operation as well. A row source generator produces a row source tree, to which what we call as a SQL execution tree, which is a collection of row sources. The row source tree shows an ordering of tables referenced by your SQL statement, an access method for each table mentioned in that statement, how Oracle approached that table to retrieve the data records from it, a join method when there are more than one tables, how they are joined together, because for an user, for a SQL developer, when I say join, for them it is a equi-join, a non-equi-join, a left join, an outer join, a self-join. But internally speaking, join is either a nested loop, join is either a sort merge join, join is either a hash join. These are the internal methods. So a join method for tables affected by join operation in the statement, and also the data operations such as filtering, sorting, aggregation, the parallel worker processes deployed if any. So when I talk about a SQL execution plan, this is in general how it would look like. I'm going to show a quick demo of it, how to obtain this. So now just to show you how things would look like, what if I want to generate an execution plan, how do I do that? So let me quickly start a SQL, let me quickly start a connection to my database. And now that I am connected, let me connect in as HR. So I am connected. This is my pretty little thing that I keep on noting every time, gives my details. Let's not bother about it as of now. I'm going to run a SQL statement, but I would also like to know what type of a plan Oracle generates for my SQL statement. So let me clear this up, and I'm planning to run this select statement. Select E.last name, J.job title, D.department name from employees E, department D, jobs J, where department ID from employee matches to the department ID from the department, and the job ID from employees table matches the job ID in the jobs table. And further, the filtering that I am only interested in records for the employee last name starting with the alphabet A. Now since I am not interested in the outcome, well, I will just show you the outcome. This is the outcome. This is how, when somebody would have run the query, he would have seen in the application. My statement must have gone through parse, execute, fetch, hard parse, soft parse, optimization, row source generation, execution, fetch, bind variables, whatnot, and ultimately the answer in few milliseconds. But no, this is not my agenda. My agenda is to understand the SQL execution tree. So apart from this, just prior to writing my statement, here I am asking Oracle, explain me the plan for, followed by my SQL statement. And it says the plan has been explained. Remember, it didn't run it. It simply says explain plan. The plan has been explained. So I'm running a script from the Oracle Home RDBMS admin UTL XPLS, so when it says the plan has been explained, it stored that plan in a plan table. Now I'm not going to write a select statement on that plan table because the plan table will present me only rows and columns. I want bit formatted output of it instead. So I'm running a utlxpls.sql script which reads the data from the plan table and presents it in a more readable and an indented manner like this. So it says here's the plan table output, the plan hash value. There's ID column where various different steps are mentioned. There are a total of 11 steps starting from 0 through 10. Then there is operation, then there is a name, there is a rows column, how many bytes, what is the cost, that is the percentage CPU utilization, and how long it took in milliseconds. And then what all predicates it considered because of my where class. This is exactly what I am referring to as an execution plan. You see, it's a very neatly indented structure. And the most indented line that I could see here is index range scan happening on my index named emp name ix, and it then went to the employees table accessing using a row ID. So I can read this plan for you as of now, or I could read it. So the same plan that you see here, instead of reading a lot of text out of here, I have documented in a diagrammatic representation here. So the most indented step that was there is this step, index range scan emp name ix, which means the very first thing, first of all, this execution SQL execution tree was given to me by the row source generator, which is collection of steps, and each step would produce some row set. Now because of the indentation that we had there, the mostly indented step is this one, index range scan. That's what I am showing here. The index range scan has first went to an index named emp name ix, looking for employee with last name starting with A. It has performed a range scan there, and then it located the row IDs of the matching records. Those row IDs were then used to access the records from my employees table. So this is way faster than instead of doing full table scan onto the underlying employees table. In parallel, at the same indented level possibly, there was another operation that took place, that is to go to the index, perform a full index scan. The index was job ID pk, must have been onto the job ID column, which is a primary key constraint, and the matching row IDs were located, and they were then used to find out data records blocks from the table jobs. So the jobs table itself was accessed using table access by index row IDs. Those row IDs came in from the index full scan. And then these two tables were joined using a sort merge join operation. So I had one row set, I had another row set coming out of different steps in my row source generation program, the SQL execution tree, and then they were joined together on the criteria that is given here. The criteria for join was job ID column of employee joins job ID column of the jobs table. This is where the sort merge join operation has taken place. And then I go here, there's another operation, that is index unique scan on the basis of department ID, which is a primary key. The necessary department were located, and once the row IDs were found, we jumped into the table, picked up from the departments table the rows with the matching row IDs, and later we joined this row source to the sort merge join operations outcome to produce the final join. And now since there's no more operation left, we went back to the select. This is the point when as an outcome I got 3 records. These are those 3 records as an outcome. So 3 records gone through 11 different minute steps. The total cost was 8. The total CPU consumption was 13%, and the total elapsed time for my query was 1 millisecond. Now this is what is called as the execution plan or the SQL execution tree. So coming back to the last phase, the SQL execution. During the execution phase, the SQL engine executes each row source in the SQL execution tree produced by the row source generator. This step is the only mandatory step in the DML processing. In general, the order of the steps in the execution is the reverse of the order in the plan. So you read the plan from bottoms up. Each step in an execution plan has a step ID, as you could see, from 0 to 10. Initial spaces in the operation column of that plan indicate the hierarchical relationships. As I said, the most indented to the least indented. So if the name of an operation is preceded by 2 spaces, then this operation is a child of an operation preceded by 1 space. So the parent would start and it would go back to the child operations. The child operations are indented to a higher degree than the parent steps. Operations preceded by 1 space are child to your select statement itself, as you could see from the SQL. So here from my operation started. So this is the parent of all, and then there is one white space, and then there is one more white space, and then there is one more white space, and then there is one more white space. So these are the child steps. So you see there's a nice indentation for you to understand in what order Oracle is going to process them. So during the execution, the database reads the data from the disk into the memory if the data is not already present in memory. Now what is this? Well, I'm preparing my ground for my next discussion, which would be on to the database buffer cache. This is the place where the disk blocks that you read from the disks are loaded into the memory. That's precisely what I said. So during execution, the database server process reads the data from the disk into the memory, provided the data block is not already present into the memory. But more on it at a later time again. So the database also takes out any locks and latches necessary to ensure the data integrity, and logs any changes made during the SQL execution. The final stage of processing a SQL statement after fetching is obviously closing the cursor. So this is overall how a SQL statement parsing happens till, well, I went beyond parsing as well to the execution phase, but my purpose still was to stick to what happens during the parsing phase. I'm going on to the next slide. I'm not going to spend much of the time here now because much of it I have already explained earlier. So I'm going to quickly talk about the SQL statement processing, opening of a cursor, parsing. Is it a query? If it is a query, then describe it. You may have to do more than one describes depending upon the complexity of the query. Once all of them has been described, you may have to define depending upon the data types to be retrieved, depending upon the bind variables. You need to ascertain the data types. You keep on doing this recursively. If there is a binding required for the bind variables that you have passed, then there's a phase called as parse, bind. So all the bind variables are bound with their values, and Oracle looks at, is it possible to parallelize the operation? Not all operations could be parallelized. So it checks on the possibility, can I parallelize the operation? Then it goes to execute. Again it checks, is it a query? And if it is a query, it fetches. The fetching also happens more than once, and there's a whole lot of cycle. So you may go from execute to parse again. This execute to parse is only required for dynamic SQL statements where the SQL statement is not known beforehand. And once when all of the fetch has been done, you go on to close the cursor. So create a cursor. As I said, creating a cursor is nothing but a pointer which points to the private SQL area memory, which is part of your PG in case of a dedicated server configuration. So create a cursor, parse the statement, describe the query results, define the query output, bind the variables, see if the operations could be done in parallel, execute the statement, fetch rows of a query, close the cursor. A more description about this flow is on to the next slide. So in the create cursor, a cursor is a handle or a name for a private SQL area. It contains information for statement processing. It is created by program interface call, by a parse call. The cursor structure is independent of a SQL statement that you are trying to run. The next step is the parsing, where the statement passed from the user process to the server process or to the dispatcher process is picked up by the Oracle instance. The parse representation of a SQL is created, and if it's a hard parse, you place that into the shared SQL area. If the library cache miss is recorded, meaning a previous parse representation is not there, then only you allocate a memory region and then keep everything into that memory region, and it can be then used by any subsequent statements, similar statements that are being that would be executed by the coming users. In the describe and define phase, the describe step provides information about the select list items. It is relevant when entering a dynamic SQL queries through OCI application. A dynamic SQL is a SQL which you don't know beforehand. There are two methods of doing it. One is either you could do it through a package called as DBMS SQL, or there is also another method called as SQL execute immediate. But let's not go there. That's a developer's area. In the define step, it defines locations, sizes, and data type information required to store fetch values in the variables. In the bind and parallelize, enables memory addresses to store the data values, allows shared SQL even though bind variables values might change. Parallelize the statements. The statements which could be parallelized are SQL, insert, update, merge, delete, create, which also could be parallelized provided it's based on some subquery. Alter, I'm assuming this alter is alter index rebuild parallelly. So these are the statements which could be parallelized to save, to deploy multiple server processes to save on the time and improve the response time and the turnaround time of your operation. And lastly, you have the execute, fetch, and close. You drive the SQL statement to produce the desired results. Fetch rows into the defined output variables that you have done here, and return the query results in the table format. And once when all of it is done, close the cursor to save the memory. Close the cursor once when the last record has been fetched. This is how the SQL statement flow is. Now a lot of it has been said. Why not do one demo on this one? So here I am trying to demonstrate DBMS SQL package where each step I am going to do expressly by writing some code. So I am defining I already had this SQL text ready with me, and I'm going to run through these steps. So here I am going to define a cursor handle, a bind variable, and then I am opening a cursor using dbms_SQL.openCursor method. It returns the cursor handle, which is a number. I could now say print. So it prints the value of the cursor handle. This is the cursor handle. I am defining a bind variable because I want to pass on some value. So just some bind variable of the type varchar2. Then I am writing dbms.parseCall, where the first argument is the cursor handle. Second one is the verbatim SQL statement. I could have stopped here also. Here, select sysdate from dual, but I deliberately went beyond and I have added a where predicate for that dummy column in the dual table, and I am passing the bind variable instead of passing a literal, and followed by a constant called as dbms_SQL.native. So I ran it. Remember, I just parsed the query with a bind variable instead of using a literal. So far, I have not assigned any value to the bind variable. Now this is for the first time that I am going to assign